everyone. Welcome back for another Zephyr Tech Talk. I think it's been a month. We've been slowing down, it seems, but pretty excited about today's Tech Talk because we have lots and lots of people. We signed up for this one. I mean, that's probably not surprising, but I hope many of you in the chat will use today's live session as an excuse to ask all the questions you might have on your mind with regards to the new hardware model that was, or the new version of the hardware model used in Zephyr that was recently introduced. As a way to kick things off, as always, please say hi in the chat if you feel like it, wherever you're joining us from. So I'm Benjamin, will be your host for today, joining for France, alongside some of our viewers from Brazil, Belgium, Florida, and hopefully many more joining soon. Eve is here. That's great. We'll talk more about Eve in a bit. Without further ado, I will be introducing our speakers for today. Please make sure to ask your questions. If you're watching the recording, you may also comment in the comment section of the YouTube video, and we will make sure that your questions get an answer. So let me bring all of our speakers on stage. Hello, Anas, Torsten, and Carles. How are you guys doing?
Hey there. Good. Thank you.
Good. Good morning.
Good to be here.
Yeah, good morning or good afternoon. We have, as always, an international crowd in terms of speakers as well, too, for today. So how about we do a quick round of intros before diving into the meat and into today's topic. Anas, I think many people might know you by now and might know your face because you've been on the show many times, but who are you?
Hey, Anas Nashif. I work for Intel. I am in Montreal, Canada. And I am the TSC chair of the Zephyr Project. I've been involved in the project almost 10 years now. Yeah, and I'm involved in many areas, also including the hardware model. I mean, the V1 and the V0 were like things I helped introduce, and I will be talking about that in a bit. And excited to see that.
We were talking about that just before going live. The fact that you can probably tell us a bit about the whole history of like how things were when Zephyr was only supporting a handful, I guess, of boards and SoCs and how it eventually evolved. Torsten, where are you joining us from, and who are you?
I'm Torsten. I'm joining from Copenhagen in Denmark. I work for Nordic Semiconductor, and I think 6 years now I've been with the Zephyr community, maintainer of the build system in Zephyr since 2020, I think.
Great, and you've been instrumental in the work that we've done around the hardware model V2. Carles.
Hey. So I'm also a Zephyr veteran, not as much as Anas, but I've been here around since 2016, so about 8 years now, I guess. And for the most part, my role with Zephyr has been bridging the gap between Zephyr and when Nordic needed, or when Nordic wanted to contribute or needed to contribute. So for a few years now, my role has consisted in making sure that Zephyr has what it needs to both be successful and be, of course, useful to the company. And we have a team, a great team of engineers, which Torsten is part of, that contribute, that are maintainers, and that do a bunch of things in Zephyr. So that's it.
Cool. Thanks. Thanks for the intros. So how did we call the today's talk? Diving into the new hardware model. So I'm assuming that many of the people joining us today are using Zephyr already, maybe just like as beginners or more advanced users. But one thing that's pretty clear when you sort of like navigate the Zephyr documentation is that it supports a lot of different hardware, right? Like lots of hardware architectures and lots of boards, lots of SoCs, I guess, in between. Anas, like we were chatting offline a bit before. Can you maybe tell us a bit? And I think you've been also like quickly digging into the history, like as in like the Git history of the project. how did things evolve? Like how did it look like at day one, like in Zephyr, to sort of target, like have the same code base targeting different architectures? What were they? Maybe also, I'm guessing Intel and ARM might have been like the first, but maybe there were more. And yeah, like, because I really, and myself, and I'm assuming the viewers as well, I would really love to understand the sort of the evolution of like how you take something that originally was a small-ish project, like a kernel and a bunch of features around it, and how you make it, like you keep evolving it over the years and still make sure that you can actually target architectures, hardware architectures that keep becoming more and more complex, right? Like multiple, multi-core and like heterogeneous architectures where you have, I don't know, RISC-V cores alongside ARM cores. So yeah, like, do you want to start like, should I share your screen? Do you want to show us what it was like back then?
Yeah, you can share my screen. Sure. So I haven't looked at this for a while. Yeah,
9 years ago.
Yeah, so I mean, even like looking at the contents of that. Yeah, this is like Zephyr 1.00. Yeah, as you see, this is the first version, which was actually released really 9 years ago. Yeah, 2016. Yeah, 8 years ago. Yeah.
I guess shortly after being sort of donated in open source.
Yeah, I mean, it was made public in February. Was it 2015 or 16? I don't even remember right now. Either way,
16,
yeah, 16. Yeah, exactly. Yeah, and just to give you an idea, I mean, this whole effort was started by Intel in basic collaboration with partners and industry leaders, NXP, Synopsys, and a few others, and Wind River was there as well. And I mean, there is no secret there that we did that to support our own products, right? I mean, this is the way we had a product coming up, and we wanted to create a community and an RTOS and do that. And this product, actually, which we were trying to support, was really a multi-core, SoC. This is this guy, yeah, the Intel Curie, yeah, very small, and this thing, as small as it is, had 3 cores or 3 different architectures. It's not only like 3 cores of the same, like x86 or something. It actually had 3 different, it's a multi-SoC, yeah, and it has an x86, which was the application processor. It had a Synopsys ARC, what we call the sensor subsystem, which actually had all of the sensing modules, and it had a Nordic Bluetooth module, right? NRF51, I think. Yeah, and if you look at the first 3 as when the project was published, that's basically this Curie thing was also launched as an Arduino board, the Arduino 101. There is also the same, basically almost using the Quark, which was like really the Intel branding. And you will notice that we have an Arduino 101 and an Arduino 101 SSS, yeah, which is basically the sensor subsystem or something like that. Yeah. And this is where basically things have started, is that we needed to support multiple architectures. You actually, to get something operational out of that, you had to build this, you had to build this. At that time, there was no Nordic support, in the tree. But later on, actually, we made it also work, and we were able, like, also to build it and bundle it and put it on the device. So this is how it started. And the surprise for me today, and I didn't really remember, was that we had all boards like under one tree. So there was no like board x86, board ARM, and so on. Everything was there. I mean, we didn't have many.
Was it even documented? Was it even explained how people were supposed to add new boards, or you were not even thinking about it just yet?
Yes, I think, I mean, I need to take a look at the documentation. I don't remember exactly right now what we had there, but yes, I mean, this is how it was launched. Like, let's say 20 boards. A lot of them are chemo. simulation, but it was 3 architecture. We launched with 3 architectures. Yeah, Synopsys, Arc, ARM, Cortex M3 in this case, which was, Freedom board, a board that we still have, and Hibit is still running as back then, and a few Intel boards, right? So this is 1.0. If you look at some point, obviously, I mean, we started getting a lot of contributions, and we realized that, okay, we have like in 1.5, I mean, not many,
more
but
boards, but still pretty flat.
Yeah, more board, but still flat. And in 1.6, at some point here, we decided, hey, that probably will not scale, and that's where we switched. In the meantime, we added a new architecture, the NIOS, which is like the FPGA. Yeah. So, and that's basically the situation as we have it probably until 1 month ago. Yeah. I don't remember actually. I think the SoC was under Arc at some point. Yeah. So we moved. Yeah, exactly. The SoCs were under architecture, and at some point we moved them up to the main tree, and we were still using Kbuild, basically the Linux kernel build system. So that was even pre-CMake. Yeah. So this is the history. Basically, just to summarize, was that we since day one we had the need for supporting multi-core SoCs and being able to build different binaries and bundle them together somehow. And also, actually, the interesting part is that these are not just individual modules or binaries that you build and they operate, on their own. There is a lot of sharing happening. So, like the memory, the peripherals, and everything is shared on the hardware. And you have to coordinate. Yeah, so you can't just build two things and have them work. There is like the memory partitioning, the flash partitioning, which SoC uses what peripheral, and so on and so on. So it needed to be actually more intelligent than just building two binaries and stitching them together and flashing them. Yeah, and that was really the pain that we had to live with until recently. Actually, SysBuild did something towards that already, like last year or a few years ago when it was introduced. But the hardware model v2 moved us away from this legacy setup that we had, and we are able now, when like if I go to where was it? How come I don't? Oh, okay. So now the boards are like here having this variant and having the x86 variant. We now have one board. I mean, if we had this board still in the tree, we will have an Arduino 101 with like in the current schema where it will have multiple SoCs, yeah, or multiple hardware or architecture or cores. Let's call it this way. And Carles will go through the terminology later because this is starting to get confusing. So you will have the Arduino board, you will have the x86 core, you will have the Arc core, you will have the Nordic core, basically, and you should be able to always, address them and deal with them and document them and build them as one board. Yeah, which in the previous configuration was a little bit complex and not user friendly. Yeah.
Right. Okay. So yeah, I mean, Carles, maybe do you want to like tell us a bit about like how, what are some of the things that eventually like made the community and Nordic in particular look at a new model and some of the work that's been done and introduced recently?
Yes, I think the key point to take into account, especially in the development of MCU type hardware, so microcontrollers for the most part in these last few years, is the emergence of AMP. They used to be that MCUs had a single core. That single core would execute everything, and you'd be done with that. So you had one target, one architecture, and it was as simple as it gets for an electronic CPU like this. But we soon hit the same wall that everybody else has hit with the the process node, with problems with power management, with delays in signal, and all of that basically has forced also the microcontroller industry to switch to a multi-core approach. However, unlike the bigger irons, right, the big chips, both the ones on mobile phones, tablets, and also on servers, which has mostly stuck to an SMP model or variant of an SMP model, meaning all of the cores can execute everything and they run at the same time and they run a single image, most importantly, right? So there is one image of code that is executed concurrently by all the cores. Yes, then you have variants like this big. LITTLE from ARM, where the cores effectively execute the same. It's just that some are better at executing slowly, but with better power consumption, and others are designed for high throughput and performance. But in the end, all cores are executing the same. The big difference with AMP and microcontrollers is that each core is different. Entirely different in many cases. In some cases, even of a different architectural altogether. But even when the same architecture is reused for multiple cores, the cores are just not executing the same code. Each core has its own memory map or memory mapped flash, typically NOR flash that you execute from, or similar memory technology. They have their own RAM, and they communicate. The cores communicate with each other, not directly through RAM, or through regular RAM, like in SMP, where everybody has access to the same memory, but rather through an IPC mechanism of some sort. And typically, the hardware assists you with that. You have some sort of mailbox, peripheral, or obviously it's called differently in each. But in Zephyr, it's called MBox, actually, the driver abstraction to implement that. And then some small piece of shared memory that's used to transmit the messages back and forth. So what that means is that essentially, if you want to run Zephyr on, say, each core of your multi-core AMP microcontroller, you need to build Zephyr multiple times, because unlike with Linux, where you build once, right, typically for what they call an architecture, but really means a family, right, of devices. Here you need multiple images, and that's the key. One of the key things that we've been addressing over time. One with SysBuild. SysBuild is a mechanism to define sort of meta builds, as in you are building one main image that has dependencies to other images. In fact, you can have as many images as you want. And this allows you, especially when using Zephyr on multiple of these cores, or many of these cores, because that's quite common nowadays. You have two cores, and one runs a typical example is one core runs the application, the other one runs a protocol stack of sorts, a Bluetooth protocol stack, or 15.4, or any thread, any of these technologies, especially wireless ones. So when you have that, you have to build Zephyr twice, once for the network core, once for the application core. SysBuild helps you with that in terms of abstracting the build system details that come into play when you're building multiple images in one go, in one West invocation, in one CMake invocation. But that was not enough.
But by the way, and sorry to interrupt, I think having a tech talk about SysBuild in the future would be really good, because I find it myself like really powerful, but it's like, where should I start? And like, there's some examples, but it feels like it's so much more powerful than what people might think at first sight. So
and we have the right person here, which is the main author of SysBuild, which is also Torsten, who will be talking later, I'm sure, about the details of the hardware model. But behind the motivation, just to finish this topic off, the fact that we had this asymmetrical devices like that with tons of cores that each is different, we had to do something about it. So SysBuild was the first step. Then I want to just give a quick shout out to the efforts we made to actually develop and complete the system device tree integration with Zephyr. System device tree is a meta device tree where you can where a single system device tree file contains the device tree for multiple CPUs, right? So that would have been perfect for us. Unfortunately, the spec didn't move quite fast enough for Zephyr, so we had to can at least temporarily. We hope that in the future we can take that again and continue the work that was started. But in the meantime, then the next big item to tackle was the boards. Boards in Zephyr, as Anas was describing, they grew up, or they evolved organically, and basically a board in Zephyr had become a build target. So something you can build for, right? A target hardware you can build for. But the problem is, like I just said, a board can have many build targets nowadays. What we call a board in the real world, a PCB with some components soldered onto it, even if it's a PCB with a single MCU, that can already have 4 cores or 4 asymmetrical cores, meaning 4 images. So that was not a good way to describe, or not an up-to-date rather way of describing the hardware, and that was one of the reasons behind Hardware Model v2. So Hardware Model v2 changes the way we define SoCs. We declare SoCs in the code base and boards. And there were tons of other improvements that were very important behind the scenes, but that probably most users won't see. But things like the architecture, we used to be hard-coded by the path, so that doesn't make sense anymore. How do you triage? How do you bin or put boards or classify them in bins based on architecture when a single SoC now can combine a multiple architecture? That makes no sense. So instead, we went from classifying by art to classifying by vendor, and there's a bunch of. But the key fundamental, the key points behind our goal of renovating, overhauling this model was this emergence of this AMP that keeps coming. Even from us and from almost every other silicon vendor out there that makes microcontrollers. There's also a couple more things that Torsten will touch upon, but I'm just going to summarize them here. There's a bunch of future enhancements that will be based on this new model. For example, being able to extend boards, which is something we've never really been able to do, at least not to that level. These also SysBuild. SysBuild had a problem because SysBuild had the concept of building multiple images, but couldn't integrate with a board with multiple cores. So that now plays well together, which is also a good match. And then all sorts of quality of life improvements that I'm sure Torsten will talk about. So that's the motivation really, and that's where we are. We're now at the place where a board in Zephyr can define any modern SoC. It goes beyond, any modern board, because it goes beyond the fact that an SoC can be multi-core. You can actually have multiple SoCs in a board now, which in some cases makes sense. And then the concept of board in Zephyr allows you to target the multiple SoCs, each with multiple cores, and each core then with multiple what we call variant that I'm sure Torsten will introduce. So that's the ideas that drove us to start this project. I think more than a year and a half ago, and then slowly maturing it, slowly bringing the attention to the community, and finally merging it just after 3.6.0 was released. So this will be in time, by the way, in the tree for LTS 3.7.0, which is coming this July, I believe. So that the LTS will contain the up-to-date current hardware model.
Great. And so quickly to go back on to your point about system device tree. So this new model was introduced with like literally zero change made to the way device tree is used in Zephyr, right? And
that's correct.
But in the future, like, would there be is system device tree still something that you think the project should consider, or might eventually?
No, absolutely. I think it's not. The thing is, what the approach we took is in order to get system device tree to work with Zephyr, was to try and collaborate with the spec maintainers. This is very much a work in progress, system device tree. That's the thing. That's the thing I may not have mentioned, made clear enough, is that system device is very new. It's being developed now by many smart people out there, but it's not ready. It's not ready for prime time, at least not for the use cases that Zephyr has. So we tried working with the upstream community, but although we did make progress, we did not make it fast enough. So at one point in the future, I'm sure that work will be resumed, and system device will be ready to be used with Zephyr. At that point, that's when we will think about probably optionally introducing it, because system device tree doesn't always make sense. It makes sense when you have a complex system with multiple CPUs, but many boards are just one CPU. So maybe system device tree will be optional in the future and opt-in. I don't know. We obviously haven't gotten there, but definitely this will continue to be in our radars because it's a good match. I mean, that's the whole point. They introduced it. The people behind system device tree were facing a very similar problem that we are facing, right? So that's the whole thing. Yeah.
Yep. So this is my call to the audience to make sure you all ask questions. We are pretty much halfway through, so we will be diving more into like how it looks like in practice to use the new hardware model. But yeah, if you have any questions, please make sure to chime in and don't wait until the last minute if you want to make sure that we take your question live. So yeah, what's next? Like, Torsten, maybe do you want to show us a bit like how it looks like in practice, the new model and some of the, I guess, the key concepts, and maybe using an existing board as an example, or
Yeah, so before doing so and showing examples, maybe it would be good to have the picture of the new description. Yes, exactly this one. So as it was mentioned before, everything in Zephyr was a board when building. Every variant was a board, every SoC. If you had the multiple CPU clusters, those would be implemented as dedicated boards as well. We had as an example, we had a MIM X8MP EVK, which was actually implemented as 4 different boards and not one board with the variants and board qualifiers. Similar with the Nordic NIF53 DK, that was also implemented as 3 boards. We had the layered BL50.
Did we just lose Torsten? Looks like we did. So, right? It's not just me, huh?
Yeah. Would you like me to continue with the basic terms, and then Torsten can take over with the actual explanation once he's back? I'm guessing that he has a connectivity issue.
Yeah, it looks like internet connectivity issue. Yeah.
Yeah, so I'm just going to go over these terms, and then Torsten can talk about the actual implementation and everything that it entails. But essentially, what happened with the introduction of hardware model V2 is that a board now suddenly was more complicated. You just couldn't use a simple name for it. You could to refer
that's
to
the
whole
point.
Itself.
Like
exactly.
It's the board plus all the things.
Exactly.
Exactly.
So before, right? We would include all of these metadata in the board name, so to speak. You would have, whenever you would refer to a board, you would have a bunch of added trailing terms that were added to make sure that you understood that the build system understood that. But here, what happens here is it's similar, but it's been formalized. It's been formalized into a format that everybody should understand, everybody working with Zephyr, and then use, because that's the whole point, is to be able to flexibly express what you want to build for while maintaining the concept of board. Like in this case, BL5340 DVK, that's the board name, right? That's what we call the board. That's what you can physically get in your hands. But then some boards have revisions. We already had support for that in HUDML v1, because sometimes things change, different revisions of the board, so you have to specify that. And then what's new here is the board qualifiers, which is essentially the SoC, because I said you can target multiple SoCs. So there are boards out there with 3 chips, one from ADML, one from Nordic, one from Intel. Then the CPU, what we call the CPU cluster. I was talking earlier about SMP. That's why this is called CPU cluster. It's because it identifies one or more CPUs operating symmetrically. So if you have a 4-core Cortex A7 running in SMP, this would be one CPU cluster. And then if you have one Cortex M7 acting as a sensor engine of some sort, that would be another CPU cluster. And finally, the variant is arbitrarily anything you want to add to that. In this case, it's being used for to implement a trusted execution environment system, where the NS is the non-secure variant of the build, because you can build for secure and non-secure targets. In that case, the CPU is further divided. The CPU cluster is further divided into secure world and non-secure world. So the variant acts there as a placeholder that you can use to put whatever you need to, but it's not tied to a particular feature like an SoC or the CPU cluster. And finally, and to give then way to Torsten, the new concept we've introduced is the board target. The board target used to be the board name and the revision. Now the board target includes the board name, the revision, and all those qualifiers. And this is ultimately what you tend to use when building, when debugging, when when interfacing with hardware in general. That's what uniquely describes the build target, so to speak, what you're building for. Right?
And to, I guess, answer Daniel's question, if I have a board that's only like there's literally just one revision, one SoC, single core, no variant whatsoever, everything's optional. Everything but the board name is optional, right? Like I could still refer.
Torsten is the right person to answer that question.
Yeah. So we have two different concepts here. One is the board target, as is showing everything here, and there's a normalized board target, which is substituting all those special characters like the alpha and the slashes into underscores, which are used internally for file names when describing config fragments and overlay files. Now, for the user who needs to invoke a build, if he is targeting a board with a single SoC, all he needs to type there is the board name, because that is, you can say, unambiguous in that case.
Yeah, the rest you can deduce. Yeah.
Yes, so you can omit that as a user convenience. But when you are describing files or creating files with configuration, then you need to provide also the SoC in the name. And one reason for that is you may come along later and extend that board. It's possible to start out, let's say, with a DK that maybe has multiple SoCs, but you are only supporting one in Zephyr for starters. That means you create the board YAML describing your SoC, and then later, when you support the other cores or the other SoCs in Zephyr, you can extend the board with those, and the rest will stay the same. Of course, at that time, users then need to specify and identify the SoC that they are building for. But as long as it's a single SoC, you can omit it. It's also possible, or will be possible in the future, like that's one part with the new model. Every time you do some changes, as Anas showed, things has been growing organically. We started out with all boards in a flat structure, later reworked into structured in architectures. Later, we started to have revision support. People started asking about variants, like more generalized form of a variant. But that was not really possible. So all of those variants got implemented as a dedicated board. And we tried to take into consideration all of those use cases and kind of unifying that. So that's why we came up with this scheme here to kind of identify the SoC, the cluster, the variant, and then let the user omit them if there is only a single SoC.
Yep.
And if it's a single SoC on the board and you have variants, you can still omit it and just use a double slash to indicate that this is the location of the SoC, but I'm building still for a dedicated variant.
Mm-hmm. Okay. There is a question from Kyle that is not strictly speaking related to hardware model V2, but that I think makes sense to try and quickly address. I think some people might simply not be familiar with what is a board revision in the first place and how one uses it. So I don't know if any of you have like a good example maybe of a board entry that uses revisions and that we could show, or can any of you quickly talk to how it's typically used. What are some the things to keep in mind when using the revisions? And yeah, I think this is a feature that people might not know exists.
There's several examples now on Tree, but the concept of revision was also introduced by Torsten. So I think it's the revision concept has been used several times, and one of the ones I know personally, if you want to basically have an example of what it would look like, is the NRF 9160 DK. This is a Nordic development kit for the NRF 9160 chip. And here you can see that we have the 0.070 and the 0.14.0 revisions.
It's revision as in hardware revision, right? Like the first version of the dev kit maybe didn't have a green LED and the next version had, right?
Exactly, that's pretty much it. And then Torsten can talk a bit more about what you can do with it.
Yeah, and you can take a look here at the 0.14.0 overlay file, and that will open up, and you see this is the difference. So if you're building for the 0.14.0 revision, then this overlay will be applied on top, because it has it's basically the same dev kit, but there's a new chip revision on this one, and there could be a little different routing on some pins. So that means you still have the same board. So this was a concept introduced years ago. We could bring up, and this is like, if we go back to the 3.6 release, Carles, if you go back there.
I have it actually open right now. I believe, yes, this is 3.6. So if I go
and then go to the same.
Back then it was, so NRF 9160, here we go, 9160 DK.
And there you already see there is two boards.
This is the effect of not having hardware v2. Go on, Torsten.
Yeah, because exactly in this case, this is actually a DK with two different SoCs that you can target. But go to the 9160, because that's the interesting one in this case. And you see here that when you wanted to do revisions, you had to create the revision.cmake below. So it would be picked up by the build system, which is very nice for the build system itself, but it's kind of problematic to anyone else, because you cannot read out that this board actually has multiple revisions. Like when you're doing a list boards, you need to know that there are revisions.
This was hidden basically in the depths of the build system instead of being available to you doing West boards or any high-level interaction with it.
Yes, and of course it was documented, but it's kind of, it's one of those organically grown things where the alternative at that time with hardware model V1 would have been to kind of create a new board, which would be even worse in this case. So we tried to unify a lot of this also with the variants. Like if you go to the, you can actually stay in the 9160.
Yeah, because this one has a variant
as well. Yeah. So you see there's _NS. And if you did a typo, let's say you want to build for a board, you would get a list of all boards, which at that time I think would print a list of 500 boards or something like that, where a lot of the boards would actually be the same. Now, with the hardware model V2, when you're working with boards, if you try to build for a non-existing board, you will get a list of boards printed. But if you try to build for a correct board, but a wrong variant or board qualifier, that could be a wrong SoC, you make a typo in the revision, you make a typo in the SoC or the CPU cluster or the variant, you will actually get just printed the board qualifiers for that board because the board is correct. So that means it's cleaner in the sense that what the board is. You know what the board is, and then you target the SoC or the variant and the revision. And all of this is now formalized in the board.yaml file. So if you go to the new model, Carles, of the 9160.
Yes. The new model would be here in main. Wait, I had it open, right? This is V6. Oh, this is the new model, actually. Sorry. This
Yeah.
is the new
So
model
you just take the board.yaml.
Yeah. This is one of the key parts of the new hardware model, being able to
Exactly.
add this metadata as part of really clearly express it in a YAML file instead of basically deducing it from a bunch of CMake variables, right?
Yes. And this means we can now pass this and we can use it in multiple different places, not just for the CMake, but also in Twister, and we can use it when we are listing boards. We can list the boards, including the qualifiers, and probably have more options in future. We have an enhancement meta issue where we are listing up some of the things we would like to introduce along the road. Because what we are doing now is that we're trying to put down a foundation where we say we know this is not sufficient for what we want to do in the future. We have had a lot of requests where we have done things on an ad hoc basis, like the extending a board today. You can actually do that out of tree, but when you do that, it will always kick in, meaning that you need to then do tricks to avoid it being active.
Yeah.
So
that's
that's
actually
not
part of the. That's actually part of another set of enhancements that built on hardware model v2, and one of them, which was just mentioned now by Torsten, is the ability to extend an existing board in a proper way. So this is going to be very useful for silicon vendors, I reckon, specifically, because for you, either for users playing around, like imagine you have a development kit, but you add a sensor to it, or you add something that's that justifies the extending an existing board instead of just using a simple overlay. It depends, obviously, depending on your use case, you might want to go all the way and extend it, or use overlays. It really depends.
Kind of the questions from
Jakub's
Jakub
question, I think that ultimately these are just convenience functions. So the reason is that then you can, of course, you could do that with overlays, but then you would have to define your own revisions of the board in a way that's just not thought or designed for that, right? Whereas here you can use the at notation, and the build system will do the proper thing. You can specify versions properly so that you get the proper error code. You can list those versions or those revisions. So the whole thing is basically integrated in the build system. You could do that with overlays, but this is a little bit like snippets, which probably deserves also its own talk, which basically is a convenient function to put together things that you could do yourself, but it would be harder and essentially not as convenient.
Yeah, and put together and give them a name, like a handle that you can use to refer to them. Yeah.
And those are things that many people do, right? Revisions, snippets, because you want to use a USB serial port instead of a physical one. So those are just things that come up again and again and again in a big project like this, and people, in pull requests, in issues, and I want this and I want this, and we, and we ourselves find ourselves needing this. So these are very good candidates for this. There's also a question
even a good example below, because during the initial hardware model v2 implementation, we got a huge discussion going regarding the chemo boards. How should we name them? Because all chemo boards right now is actually having its architecture in the name, because they are still implemented as different boards, simply because the alternative would be to place all of this in a single folder, which would create a different kind of mess. Now, with this approach, we could actually clean up that as well and have a chemo board, and then have the different SoCs for the chemo boards in different folders. I think I wrote that as an example below.
Here it is, yeah. So the chemo boards where you could QMR, QMRM, yeah. That this is the current situation. The future would look like this. The future
could look like that, yes.
Yeah, exactly. Yeah. Because if you haven't looked at that, I suggest you go into the QMO board folder, and it's quite the thing. So yeah, there's a lot of complexity there.
Yeah, we needed to kind of say, okay, this is what we do now, and then this is for the future enhancement. Yeah, and as well as also as Carles mentioned, the sysbuild in this case, sysbuild had to kind of do all sorts of tricks to be able to kind of swap a board, and you need to test specifically for boards. Now you can actually say that if you are building with sysbuild for a given SoC, well then if I know I'm building a multi-image with the MCU boot, or I'm building a non-secure image and so on, I can actually test for the SoC, and I can adjust just the qualifier and reuse the board, because I know that on the SoC, if you have multiple CPU clusters, you inherit the cluster from the SoC, and you can then adjust the qualifier without modifying the board, and then get the supporting. Let's say if you have an SoC with 2 cores, in this case an app core and a network core, well, you can say that, okay, I just adjust and I build my Bluetooth host for the application, and I build the controller for the network core, regardless of whether it's a Nordic board or a layered board or a board that is a custom board for the user who uses the same SoC. He gets the same possibilities of addressing the other core in sysbuild.
Kind of related, there's this question from Louis where like, what happens when you have a multi-core SoC? Is there a way now with hardware model V2 to make it easier to configure shared peripherals that like you want one core, like the network core, to have access to a subset of the GPIOs maybe, or like those kind of scenarios? Is there?
I think that's system device trees territory. That's
Sure.
that's because that's where you have system device tree exists also as in part to declare how the common hardware is split across different cores. So that's one of the major points. So I think while I'm sure Torsten can name one or two things about how Model V2 that will make this easier, the key thing here will be to have a meta device tree where you can say this particular mailbox belongs here, this UART belongs there, and that's what you can do with system device tree, right?
Yeah, and that was why we actually waited a long time before. Like we had the initial idea of, we started out with sysbuild, and then we had the initial idea of hardware model V2, but then it kind of was paused for a long time because work was ongoing with system device tree, which we really wanted to have in because it would address a lot of those issues. But at the end, we needed to say, okay, we need to continue with hardware model V2 and then wait for system device tree later and adapt that when it's ready and when we can use it in our needs, for Zephyr needs.
There's a whole rationale and in the links. If you know in this main page from here, you can go to the original issue and jump to the system device tree one and read more if you're interested. There's links there also to the system device tree project on GitHub. If you want to discuss and you want to contribute, then I'm sure they will welcome your contributions. And it's a project that will certainly pick up steam in the future because the people driving this, they're doing it mainly for Linux to build multiple Linuxes and combine it with also embedded builds. But for embedded builds, it's perfect. So as well for builds without big cores. So yeah.
On the topic of terminology, I guess, to some extent, and best practices, Ryan is asking for module vendors, like, and we have in tree modules from like rack wireless, where you have like an MCU coupled with a LoRa radio or an MCU coupled with a cellular modem. With the hardware model V2, are those modules effectively going to become boards, and then you can reuse the module definition? on the actual board that uses the module, or like what are some what are your thoughts or recommendations there?
That's a very good point. I don't know, Torsten, what do you think? If a user is using a module and you want to import that, I guess it will be the extend function, no? Or how would that work?
Yeah, that would probably could be a good use case for the extent.
Yeah. So this,
and
as a reminder, this is not implemented yet. This is
Okay.
one of the follow-ups after hard
Yeah.
model v2 settles.
Yeah, and it kind of maybe we should have this as a dedicated extension,
Mhm.
just to kind of be aware about it. And of course, it would be nice to do both at the same time, but to not forget it, because that's a very good point. It's kind of in some ways related to the zip concept, and
Mhm.
a concept we didn't address with hardware model v2, but that we have noted down, and is something to look at in the future, because a zip can actually contain multiple SoCs, or multiple different zips could contain the same SoC, something that you cannot model today. And that would kind of be one more level. And that was also brought up. And that's also one of the enhancement issues that we have.
Mhm.
And just to make sure we address Daniel's question, and speaking of the model and the concepts there, question is, does hardware model v2 still follows the hierarchy as listed here? I would hope so, because we refreshed this part of the documentation recently, but
Yes.
Yeah, it does. It does, because this is mostly about the hardware, not about the files. This image depicts hardware, not files. If it were files, then it wouldn't be true. But what we're saying here is commonality, and there's an architecture, and then you can have, in this case, both CPUs are the same architecture, but you could have multiple architectures here. And each the CPU concept here is slightly different than what we've been using, but essentially it's the same. Essentially, it's the same idea behind a CPU cluster. And then, because a CPU cluster needs to be part of an SoC family and series, and then the SoC itself, this is a little bit misleading. It's made be clearer if you look at the list that we have here in the hardware hierarchy. Where is this? Here. Sorry, it was recently reworked from bullet points to a paragraph. So I think the best way to read this diagram is to actually read this text, right? Because it gives you the relationships between the different items that are drawn here. So each board has one or more SoCs, and then each SoCs can be optionally classed into an SoC series, because many SoCs can be grouped into series, and vendors do group them into series, right? Which in turn may optionally belong to an SoC family. So in again, that's something like I was going to use Nordic. I'm trying not to use Nordic. So if someone has a better example with a non-Nordic, so in Nordic we have the NRF series, but then the NRF family, and then we have the NRF 52 series, and then inside the NRF 52 series we have the NRF 52832, which is an SoC model, right? So this is the hierarchy. But then inside an SoC, then you have one or more CPU clusters, as we defined, and like we said, each containing one or more CPU cores of an architecture. So it's kind of, so first of all, yes, this is applicable, but I recommend looking at this diagram with the text that describes it.
Yeah, Carles, I think actually just looking at this right now, I think we need to change this. Yeah,
Okay.
This is when you look at the top line, the board, and then implementing one SoC. It's the one that would be like the same board, like I was showing earlier, or how we have been doing. Board right now can sit on top of two SoCs, yeah. So, or three, or
it's
four.
a good point.
Board X, board Y. We should just show some examples.
I remember doing this chart long time ago. Probably it worked for a while. We need to change that. Yeah.
I missed this because I was thinking about the hardware and not the but you're completely right.
Yeah. And there was, and it's kind of an implementation detail, I guess, but kind of related to the SIF discussion and those kind of scenarios. Is there, like, would there be a problem if one would be to describe and to model a board when they have several instances of the same SoC? I.e., is this possible to
That's
have
actually a very good use case. That's not directly possible today because when you specify an SoC in the board.yaml, it needs to match up towards the SoC in the soc.yaml. So you can actually not specify two of those.
Right. We haven't talked about
No.
SoCs today, not much, because most people are involved directly only with adding boards. It's rare to make your own SoC, but it's rare and not impossible because we
but if the board has multiple times the same SoC, this might also be a constraint.
I was just gonna show briefly an example of an SoC going back to the same of an SoC folder, sorry, which has also changed.
Yeah. So what you can do in that case is that you can create two board variants because the build itself is kind of the same in terms of the tool chains and the K configs and so on. And then you would need to target the two SoCs differently using the variant if you want to have variation in the build. And then you need, when you are flashing, to know which of the two SoCs you actually want to flash.
Yeah, because you need to assign some sort of name, right? That's the thing.
Exactly,
So when building for it, it wouldn't be enough. But it's it's a really interesting use case because we honestly no one has thought of that. This has been brought up for the first time. It's great that you asked this. You can file an enhancement request on GitHub because Torsten, I can imagine that we could do something like assigning for these cases assigning a friendly name to the SoC. I don't know.
You would still need to decide somehow which of the two SoCs on that board you're actually targeting.
Yeah, I know, but
both
I
for
mean,
the build, the build is easy in itself, but also when flashing.
Yeah, indeed. Yeah.
As we will be running out of time in a couple minutes, maybe Carles, can you show us, like, for folks who might have existing boards they've been working on and like integrating basically their own PCB and their own design to Zephyr, like what would be the best way to for them to migrate to hardware model v2? I think there was this like we have an example application, right? Like a Zephyr example application where maybe this is a good starting point, right?
Yeah, actually, well, first of all, I recommend users that are looking into porting their boards to the new hardware model to look at the documentation. This is in the board porting guide. There's a section on the hardware on the current hardware model, which is V2, obviously, and then in there's a link. There's a link to one particular commit or pull request rather. Which is this one. And this shows the changes that were required in order to port an imaginary board that we have in this example
what
application.
Files you need to move, what files
exactly.
you need
The rename that have this. So this was deleted, this was renamed, and so on. So this, I think, is the best short overview on what you need to change, right, in order to transition to the new hardware model. Additionally,
and it's not a lot. Like we can see on the left-hand side, it was mostly just moving
like
things
you can
around.
Say you can see there's one deletion, some changes, or rather an addition, and then the others are mostly renames with some slight changes in them. So the changes are minimal. Of course, that doesn't count, or that doesn't take into account the more complex use cases, which the hardware model is designed for. This is only for simple boards with a single SoC and so on. And then what I wanted to highlight as well is that there is a conversion script that was contributed also during the hardware model development. That can be found in the main tree in script utils board v1 to v2. Again, it's linked from the same section, so I definitely recommend going here first. And then this script helps. It will do essentially this port here was done with that script, meaning that for simple use cases it will work. Or it should work out of the box. It does not handle the more difficult or complex cases, but it's a good starting point. It's a good starting point if you have a board that you want to port over to hardware model v2.
Yeah, you can say the three main bullet points for changing from a V1 board to a V2 to the V2 model. That is creation of the board.yaml file, which describes the meta information of the board. Then it is removing the SoC and board settings in the def config, because it used to be so that all boards and all SoCs were inside choices, which you cannot select in kconfig. So those had to be done as a config underscore board name equal y, config underscore soc name equal y. And that had actually some drawbacks as well. So those are now being done as proper selects. So that is the third thing you need to do. In your kconfig.board file, you need to use a select instead, and that is what you see now. So when you have the config board,
here, exactly here.
And it's no longer a bool because this is being defined by the build system automatically.
These are some of the changes we were talking about in the very beginning. We say a lot of quality of life improvement. They're not only quality of life. This is a cleanup. This was all a little bit clunky. So this was a cleanup that had been in the plans for ages and finally took place.
Great. Yeah, and with that, I think we're out of time. I hope and I think we've addressed all the questions that came. Hopefully, we shared just enough pointers for people to get started. I will just put briefly on screen a quick plug for the next Tech Talk in slightly over 3 weeks. Be careful if you're sort of a regular. It will be on a Thursday this time. So in 3 weeks' time, 3 weeks and a day, we will have Ev to talk about kind of a nice follow-up actually to the hardware model V2 discussion. Talk about what it takes to bring up a new board to Zephyr and what are some of the things you can take inspiration from with what's already in the tree. What are some of the hidden gems in terms of some existing code samples and tools like the shell that we've been talking many times about. I'm really looking forward to this one. It's not live just yet on YouTube and LinkedIn, but it will be shortly. So remember to RSVP to make sure that you get the reminders. And if you're interested in speaking at an upcoming Tech Talk, you can also always reach out to me. And with that, was there anything else that you guys wanted to share? Carles, Anas, Torsten?
Oh, as usual, we welcome feedback and contributions to this new hard model. It's brand new. We're still settling. We still have a few things that are in flux currently, and obviously we will resolve them all before LTS. But if you want to chime in, of course, you're always welcome. Discord, GitHub, and anywhere else, mailing lists, to give us your opinion, send patches, whatever you prefer. Thank you.
Yeah, we are all on Discord. That's usually the call to action. Come and find us on Discord. Thanks, guys, and thanks everyone for watching. We will be back in a few weeks. Bye.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.